Il est pas vert, il est pas rouge, il est orange en fait. Là, c'est blanc.
Il est blanc, ouais. Quand c'est en train de se connecter, qu'il doit donner tous les... Oui, non, peut-être.
En fait, il y a des problèmes avec Crénataire. J'ai vu ça en fait. Il y a des collègues brésiliens qui ont des soucis en fait pour.
Ah ouais.
Ouais. Pour envoyer des mails. Hein.
Là, j'ai un écho incroyable. Ah, mais c'est parce que tu streams sur
Je viens de
YouTube,
démarrer le stream du son pour tester. Ma caméra ne fonctionne pas sur YouTube.
Faut faire attention à ce qu'on dit, on est streamé là.
Rouge.
Hello, Abhinav. Can you hear us?
Hi, Arno. Yes, I can hear you.
Awesome.
Perfect.
Attends, 2 secondes, je sais pas pourquoi ma webcam ne fonctionne pas, je redémarre OBS.
D'accord, pas de problème.
Ok, ça va marcher maintenant.
Ouais. So, does anyone in the committee has any question on the way things are going to unroll regarding webcams and microphone? Or is everything clear for everyone? If so, then I yield the stage, Jean-François. So I think Tom is streaming online now, and let's start.
Yeah. So in 1 minute, we can start. Okay. Perhaps we can present every member of the committee. Perhaps we start with Christian from Paderborn. You can shortly present you, Christian?
Yes. So thanks for inviting me to this committee. My name is Christian Plessel. I'm a professor for high-performance computing systems at the University of Paderborn in Germany.
Yeah, thank you. Patrick from CEA.
Yeah, hello. So I'm Patrick Caibo from CEA, research scientist over there, working on R&D on next generation of supercomputers.
Thanks. Camille?
Sorry. My name is Camille Coty. I'm an assistant professor at University of Paris 13, now called University of Paris North, Sorbonne Paris North.
Thanks. Amila?
Hi, my name is Abhinav Bhatele. I'm an assistant professor at the University of Maryland.
Okay. Amila?
Hello, I am Amina Garmouche. I'm an assistant professor at Télécom Sud Paris, and I'm currently working at INRI at Bordeaux.
Thanks. Arnaud, perhaps.
Okay, so my name is Arnaud Legrand. I'm a senior research director, and I'm the thesis advisor of Cornebize.
Okay. Jean-François Méo, I'm professor in Grenoble, Grenoble University. So I am the president of this committee. So Tom, so you can start. You have 45 minutes after we can discuss with you. We can congratulate, we can make some criticism. Yeah, everything is possible at the end. Okay, you can start.
Thank you. So hello everyone. First of all, thank you all for attending my PhD defense. In particular, thanks a lot to all members of the jury for accepting to be here today. In this presentation, I'm going to present you my work on performance prediction and experiments. For a long time now, science has relied a lot on computations. Already 2 centuries ago, there were people employed for calculating by hand a lot of arithmetical operations for scientists. Eventually, they got replaced by machines, which became gradually more advanced. In the last decades, we have seen an exponential increase of computation capabilities of these machines, and this is mainly due to Moore's law. This huge performance improvement had led to impressive scientific breakthrough. I'm giving an example here where 20 years ago, it costed $100 million to sequence an entire human genome, and nowadays it's only $1,000. The problem that you need to understand, however, is that because of this complexity, we have a lot of troubles to measure the performance of computers. Processors nowadays are extremely complex. They have several cores, several caches, vector instructions, dynamic frequency scaling, and the supercomputers like this one have thousands of these processors. So I said extremely complex machine and difficult to measure performance. In fact, we have quite a similar problem to natural sciences. Whenever you have a complex object, you will have variability and opacity, and so you do not have perfect understanding of what's going on, a perfect model of what you're observing. And for this reason, we need experiments. So even though computers are made by humans, so they do not obey any unknown natural laws, we have no choice but to study them empirically because of this complexity. Now, these empirical studies can be done in reality, so just take a program, a computer, run the program on a computer, and measure its performance. But as we see during this talk, they can also be done using a simulator. But first of all, a bit of context. I'm a scientist, so I run applications on a supercomputer, and before even running my application, I need to figure out a few things. First of all, how many nodes do I need? Is it 10 or 100 or 1,000? Then, how long do I expect my application to run? Is it 1 hour or 1 week? These questions are important because if I get them wrong, this could lead to a big waste of resources. Then my application has several parameters that I can tune to try to improve its performance. And I need to figure out the best possible combination of these parameters. After my application has terminated, I have one more question usually is, did I get expected performance? Because there could be a performance bug in the application itself. There could be maybe a misconfiguration of the platform that could lead to a poor performance. And so what people usually do is that they do a lot of large-scale runs just to try to tune performance and understand a bit better what's going on. So my holy grail today will be to do predictive simulation. Just run my application on a simulator on my laptop, for instance, and get a good estimate of what's going on. What I'm going to show you today is that to do so, it's extremely important to capture the whole application and platform complexity. So the goal is to predict the performance of a parallel application. For this, we chose high-performance MinPack as a case study. So this is a famous benchmark. We did extensive validation by comparing our simulations to the reality to see if this matched or not. By doing so, we demonstrate that, yes, indeed, it is possible to predict faithfully the behavior of complex parallel applications. There are two important points toward this goal. First of all, it's extremely important to model correctly the platform variability that you're trying to model. And second, a lot of care needs to be taken in the experiments, the calibration you do of the target platform. To this end, we made a lot of automations of our experiments and statistical analysis. We worked also a lot on experiment methodology because even in computer science, we have a lot of experimental biases that we needed to overcome. And finally, we implemented performance non-regression tests because you really do not want your platform to change in the middle of the study without you being notified. Yes, unfortunately, due to time constraints, I will not be able to go thoroughly through these 2 points here. So let's talk about performance predictions and simulation. This work is based on a SimGrid simulation framework. So this is a 20 years old project. And on top of this framework, the SimGrid team has built a SMPI simulator. So you can see it as a full re-implementation of the MPI standard on top of the simulator. With this, you can simply run unmodified out-of-the-box any C or C++ code, and you just have to replace MPICC MPI run by SMPICC SMPI run, and that's it. You are done. How it works is that the whole application will run for real on your laptop, for instance. All the code will be executed. The communications will be faked. So whenever there is an MPI send or MPI receive, it will be replaced by some good network model. And of course, as a user, you need to provide a performance model for the target platform. For instance, giving the network bandwidth or the network topology. Until now, all the validations of SMPI were done using simple applications. So one of the contributions of the thesis is to validate SMPI on a more ambitious application. So for this, we chose high-performance LINPACK, which is more ambitious, mainly because it employs some state-of-the-art techniques to reach the best possible performance. For instance, they overlap computations and communications in the benchmark with some custom collective operations. For this reason, this application is more representative of some other HPC applications. And in fact, it's well established. That's the benchmark used to rank the fastest supercomputers in the world in the top 500 list. A quick word on the benchmark, on the algorithm behind the benchmark. So in input, it takes a large matrix A, this one, and it factorizes it into two triangular matrices L and U. There is some outer loop, and in this loop, you will have some allocations, some factorization, some broadcasts, some local updates, etc., etc. And as a user, there are several parameters that you can tune to try to improve the performance of the application. First of all, there is the process grid. So in HPL, all the processes, the MPI processes, are organized in a 2D grid. You have P rows and Q columns. And as a user, you can control the width and height of this process grid to have more like a rectangle or a square. Then there is the block size. Block size is this NB that you see here, and this basically controls the granularity of your algorithm. Then there are 6 different broadcast algorithms in the application. So they, in fact, they implemented their own custom collectives. That's what I told you about, and you can choose between any of them. There are a few other parameters, and in the end, you have like hundreds of different combinations of all these parameters. I told you in the previous slide that in SMPI, in the simulator, when we run the simulation, all the code of the application will be executed for real on your laptop, for instance. So this works very well at small scale, but if you want to reach a larger scale, like a supercomputer, of course, it won't be feasible anymore. First, the simulation time will be simply too large. I'm talking about hundreds of days. And then, in fact, you could not even run it because you will need to allocate the large matrix A, and it won't fit on memory of your laptop. So we made a few contributions. One of the first contributions was to apply a few modifications to HPL code, to make it possible. And one of them was to skip the expensive computations, because here you need to understand that we are not interested in the actual result of the application, but more in estimating its total duration. So if a piece of code does not affect the execution path of the rest of the application, we can safely skip it and replace it by a model. This is what we did. We replaced the djump function, for instance, So now I will talk about the model that we used to replace this function, how we estimated the duration of the call to the DGEM. So for those who don't know, DGEM is a matrix product. So take two matrices of size m by n and n by k. And the amount of computations done by this function is proportional to the product m and k. So one first naive model is to suppose that the duration here will be proportional to the product here m and k, so you get one straight line like that. But of course, this is a naive model. We made some measures of the DGEM duration on our cluster, which has a lot of processors, and we observed this. So yes, this is linear, but we still have quite a lot of variability that we would like to capture in our model. So I said that we have several processors. They are all the same, but in reality, you still have some heterogeneity. Some processors will be a bit faster than others. This is what we see here. We colored each processor with a different color, and there is one line per processor, and we see that some of them will be faster than others. So the first refinement for our model is to use one coefficient per processor here, instead of having one global coefficient. Now let's have a look at the same data, but only for one particular processor. So the red points that you see here are the real durations of the DGEM function. And the black line is our current model. So this is one of the lines that you had on the left. What we see on this plot is that there are some points, for instance, this one, that are quite far from the black line. And in fact, these points have been obtained with some weirdly shaped matrices, very elongated. And with this kind of matrices, you have very poor performance because of memory effects. And of course, we cannot capture this kind of phenomena if we use only one coefficient in our model. So for this, we had to introduce the other terms of the polynomial, like mn, nk, etc. By doing so, our new predictions are the blue point that you see here instead of the black line. And you see that these blue points are much closer to the white points than what we used to have with the black line. So that's already much better. Finally, we modeled the remaining variability using some random normally distributed noise. And here, the new predictions are the orange points that you see, and it's even more realistic. We can reproduce this variability in our model. All right, that's it for the computation models. So now we'll have a look similarly to the models for the communications. This could be important because, as I said, in HPL they have their own non-blocking corrective operations, so maybe we should take some care with that. Similarly, we measured the duration of important functions like MPI receive, MPI send, and here in the y-axis you have the duration, and in the x-axis you have the message size. And be careful, this is a log scale, so that's why we have some weird shape like that. The first natural model for this modeling your communication is to say that the duration of the communication will be proportional to the size of the message. But we see here that in some points, for instance here, the duration will suddenly be much different, just changing message size by 1 byte. So the first refinement for our model is to use a piecewise linear model instead of the usual linear model. Then here, for instance, we see that the noise that we have is weirdly shaped. Sometimes you will get lucky and the communication will be extremely fast, but sometimes you will not get lucky and it will be much slower. So here what we did is to model this as a mixture of normal regressions instead of having just one normal regression or even no randomness at all. All right. We have our models, and now the goal is to validate them. For doing so, we will compare our predictions to the reality to see if this match or not. And here, what you need to understand is that to validate the model, you really have to push it to its limit, to try to break it That's the only way we can do so. So the first validation is a qualitative validation. Here we ran a HPL application for real on a real platform, and we stopped it at the 5th iteration. On the y-axis here you have, so in this Gantt chart you have all the 256 MPI processes, and here on the x-axis you have all the duration. In yellow you have the computations, so mostly DGEM function, and in red and purple these are the communications, so MPI send, MPI receive. Next we try to make the same thing but in simulation, using the simplest model for both the computations and the communications. So here in this model, we use only one coefficient. There is no randomness, there is no heterogeneity. We get this figure. So here, what's already very good is that we can distinguish very clearly the same algorithm structure. In both cases, we can see pretty well the 5 iterations of the application with this alternance of yellow and red. So that's already pretty good. What's more disappointing is that the prediction of the duration of the application, the black line here, is quite far from the reality, the black line that we have here. So that's a bit disappointing. And the reason for that is that the red zones, for instance, this one, the communications, are shorter in simulation than they were in reality. So this is why our prediction does not match. So the next step to try to fix this was to make the same simulation, but using a more complex model for the communication, with the randomness, the noise that we inject in the estimated durations. And we get this. Here, this nearly did not change. The Gantt chart that I'm presenting here is nearly identical to the previous one. The prediction is the same. And so the network is clearly not the culprit. Next step, we tried a more complex model for the computations. So we introduced the heterogeneity and the randomness in the estimated durations for the DGEM function. And we get this, which is much more satisfying. Now the black line here is much closer to the black line that we had here. And what we see is that, strangely, by changing the model we had for the communications in red, affected, changing the model that we had for the computation in yellow, affected the estimation for the communications in red. And the reason is that by introducing some variability in the computations, this led to some synchronization issues in the application itself, some late send and late receives. And this was obviously important to capture this kind of phenomenon in our model. All right, so now we'll do a more quantitative and more broader validation of the predictions. Here we ran the high performance min pack for until the end, so we stopped skipping it at the 5th iteration. So until the end, and we ran it for different matrix sizes. So this is what I'm showing here on the x-axis. The y-axis, you have the performance reported by the algorithm when it finished, and we repeat several times the run of the algorithm for each matrix size. So these are all the points that you see here on this figure. So next, we try to do the same thing, but in simulation. Here again, we use the most simple model we have, so only one coefficient. There is no randomness at all. And as before, we are too optimistic. Here, the prediction error for the largest matrix is 33%. So again, that's a bit disappointing. But then we tried a more complex model for computation. So we introduced some heterogeneity. We use one coefficient per processor instead of one global coefficient. And that's already much better. Now our prediction error is 9%, which is much more satisfying. Finally, we use an even more complex model by adding some randomness in the durations of the DGEM. And this is near perfect now with a prediction error of only 1%, just by adding the remaining variability. So here the message is, yes, we managed to have very accurate predictions. And it was very important to model accurately the spatial and temporal computation variability. But maybe we got lucky. Here, this was just one particular configuration of HPL, and I told you that there are a lot of them. So next step in our validation was to validate our predictions on other configurations. In this figure, I change the process grid of HPL. So remember I told you the MPI processes are organized in a 2D grid. And so sometimes your 2D grid will be more like a square, and P is approximately equal to Q. And sometimes it will be more like a very elongated rectangle, like here or here. And in this configuration, you have a very bad performance. This figure, we see that the predictions in orange are extremely close to the reality in green. So again, very good predictions. The perspective for this kind of study is that we could use our predictions to do some geometry tuning of the application in simulation before even running it for real on a real platform. So now we do some, we compare predictions and reality with changing the other parameters of the algorithm. So here we change 4 of these parameters for a total of 72 combinations. For instance, there is a block size, which has 2 different values here. And there are also the 6 broadcast algorithms that are presented as the columns. You see the alternance of white and gray. And we see that we have pretty good predictions everywhere. The worst one are these predictions here, where we get an error of 15%, which is not too bad. And all the other ones are extremely good. One perspective for this kind of figure is that we could use our predictions to do some parameter tuning, again, to try to choose the best possible combination of the parameters in simulation before even running the application for real on a real platform. This figure is the one that I showed you a bit before, where we change the matrix size and we look at HPL performance. And during this thesis, at some point, we had one problem where 4 nodes of the cluster had a cooling issue that caused some overheating. Because of this overheating, the nodes went slower, and so the whole application went slower. So of course, now our predictions were completely wrong. To fix that, we simply had to measure again the duration of DGEM on these 4 nodes to update our model and to run again the simulations with this updated model. And by doing so, we get this new simulation in orange, and again, it's very close to the reality. So the message here is just updating the model to take into account the platform change was enough to get back extremely good predictions. One perspective of this is that whenever prediction disagrees with reality, it can often mean that there is a problem in reality, in the real platform, and that maybe you should investigate to try to understand why this does not match. Okay, that's all for the validation. So now this is just a small use case of our predictions, a sensibility analysis. In this what-if scenario, we asked ourselves, what if the network topology of my cluster was different? So we take a 2-level factory and with 4 top-level switches, and we try to remove one of these top-level switches one by one and see how it affects the performance of the application. This is a very classical study that has already been done in several papers on real platform, and we just try to reproduce this on simulation. Our conclusion is similar. If we remove only one switch, like this one, well, there is no effect on HPL performance. The overhead is 0. If we remove 2 switches, it starts to become noticeable, but it's quite reasonable still. But then if we remove 3 switches, it's quite worse. Message here is that we have a faithful surrogate, a very nice tool that we can use to do a lot of different studies, empirical studies of hypothetical platform or even extrapolations of existing platforms. So, goal accomplished. We managed to have some very accurate performance predictions of high performance lean pack. We did so in a low cost because a simulation is always cheaper than a real run. and with a very low amount of modifications in HPL code. So we could apply a similar approach to other kind of applications. But the devil is in the details. To reach this kind of accuracy, we had quite a lot of troubles, and it was very important to overcome them. First, in the calibration, the measures that we made for DGEM and MPI, and then about the platform change I told you about, the coding issue. So first, the calibrations. When we measure the duration of DGEM or MPI functions, we experienced at several points during this thesis some experimental biases. Here, I'm talking about some real effects on the durations we measure and also on some system metrics like CPU frequency. So this is really not a statistical artifact, but a real experimental bias. The first one was that when we measure durations of DGEM function, we have to measure it for a lot of different matrix sizes to compute our model. And the way we generate this sequence of matrix sizes can affect quite significantly what we are measuring, the performance we are measuring, and also even the frequency of the CPU, for instance. For example, fixing one of the sizes to some constant and just generating randomly the two other sizes can affect drastically what you are measuring. Talking here about 10% of systematic performance change. Then, I told you before, when we measure the DGEM function and the MPI functions, we did this independently, because here the assumption that we made was that the communications and computations did not interfere between each other, and that we could measure them independently. This is true for most configurations of HPL, but for some extreme configurations, this hypothesis does not hold anymore. And I'm talking here about a very elongated process grid with very small p and very large q, for instance. And in these particular configurations, we have observed for real interferences between computations and communications. So to fix this, we had to add in the code that we used to measure the MPI durations, we needed to add some background computations to have a more realistic calibration code. Last, in the code that we used to measure the DGEM duration, at the beginning of this thesis, we used to fill the matrices with some constant value, so 42 everywhere, for instance. And our predictions for the duration of DGEM did not match exactly what we observed in HPL. So we investigated a bit, and eventually we found out that if we change the content of the matrices and we fill them with random values instead of constant values, well, this affects significantly the performance of DGEM. The reason is that when your processors make some computations on variable data, they will use a tiny amount additional energy in comparison when they handle constant data. So here, this is a small change. I'm only talking about 5% systematic performance change, but this was very unexpected for us. We are quite shocked, in fact, to see that changing the content of the matrix could affect the duration of matrix product. Message here is that this kind of biases could only be identified with a very solid experimental methodology, with a lot of randomizations in appropriate places. We could never have observed this kind of phenomenon with a poor methodology. Then, in some configurations, experimental bias may be desirable to increase prediction accuracy. For instance, the sequence of matrix sizes that you use to measure the DGEM function should be reasonably close to the sizes that we observe in HPL. The distribution should be reasonably close. So now we have quite a strong experimental methodology. We have avoided a lot of problems, but we still had one issue during the thesis where the platform changed. And in fact, we did not notice immediately. So we lost a lot of time because of this, just to try to understand what's going on. Why our predictions are different. So to avoid this problem to repeat itself, we implemented performance non-regression test to always be notified and to always have an updated model every day. For this, we took the DGM calibration code, so the code that we use to generate our DGM model, and we ran this code on a near daily basis on the different clusters of grid 5000. Here we use different clusters because we experienced some problems on one particular cluster, so we figured that maybe there could be some issues with other clusters. And I'm talking about 30-minute jobs, including node deployment, warm-up, and experiment itself. So for each CPU of this cluster and for each job, we collect the average DGM performance, the DGM coefficients of reduction. So here are the coefficients that we use in our model for the simulation. And then several system metrics like CPU frequency, CPU power consumption, DRAM power consumptions, and average temperature. So all the variables that I'm showing here, all the parameters that we collect, these are averages for on a peer CPU and peer job basis. Now, if we make the assumption that the platform did not change, then we can assume that these parameters will be normally distributed thanks to the central limit term. But again, this is assuming that the platform did not change. If it changed, then we can expect that the new observation will be quite far from the distribution that we used to have. So, how to detect a change? Well, let's say we have a sequence of old observations like H1 up to Hn, and one new observation, Hn plus 1. Then the question is, how likely was it to observe Hn plus 1? So if this is our distribution, and we have one new observation here, well, this one was likely to be observed, there is no problem. But if our new observation is here, well, maybe there is an anomaly because it's pretty far from the distribution. So this is very classical statistics. We just take the sample mean and sample standard deviation, and we use the distribution to compute the probability. One technical point is that we use the F distribution instead of the normal distribution because we do not know the true mean and true standard deviation of our data. We have only the sample mean and sample standard deviation. But this is only a technicality. Regression coefficients. And so maybe we could use the relations that exist between these parameters to have a more powerful tests. This is the idea here. So here, in this example, we have two different parameters. So this could be two different coefficients for the linear regression, for instance. One here and one here. The old observations are the black points that you see here, and we have two new observations, the one here in orange and one here in green. Now, if you look at the two parameters independently, the conclusion will be that these two new observations were completely expected because they are both in the fluctuation interval if you look at them independently. But if you use the information you have and you look at these two parameters together, then obviously the orange point is an anomaly because it's outside of the ellipse. It's quite far from the old data. And the green one is perfectly normal. It's inside the ellipse and it's close to the other data. To compute this fluctuation ellipse, we use the covariance matrix of the old data. And so here it is in 2 dimensions, but we can generalize it very well in arbitrary dimension. So let's have a look at some real data. Here we are back in 1 dimension. In this axis, here we have the average DGM performance. In this axis, this is the date of the experiment. And all the points that you see are therefore the average performance on this particular node on a given day. The gray ribbon that you see, the gray zone, is the fluctuation interval I told you about. And whenever a point falls outside of this interval, it will be called differently. It will be either in blue when it's below the interval or in red when it's above. When this happens, we will get notified and we will investigate to try to understand what's going on. Then we may decide that, yes, the platform has significantly changed, and so we will put a vertical line like this one then we reset the fluctuation interval because this has changed. For instance, here we had a cooling issue that I told you about, and the platform, the performance was significantly lower. Here the cooling issue was fixed and the performance was higher, and in between we changed our experimental protocol that affected also the performance. So this was one cluster, one node of the diode cluster, sorry. Let's have a look at another node of the same cluster. So first here we see that there is no cooling issue here, but there are some weird points here near the end. You see that sometimes the performance is pretty low in these zones, and sometimes it's higher. The story behind this is that the GRID 5000 staff added a new cluster in the same machine room as the diode cluster. And this new cluster has an extremely large power consumption. And whenever it is booted, it interferes with some nodes of the diode cluster. So here, when the point is low, it means that the new cluster is booted. And when the point is high, it means that the new cluster is not booted. So you see, this is not a permanent change. This is more like a sporadic problem that happens. So here we decided to not put a vertical line and to reset the fluctuation interval for that, but rather to label these points as outliers to exclude them from our reference set that we use for the fluctuation interval. Now, one question you may have is, well, what if the change that happens on the platform is more subtle, a very small change? This is kind of what happened here. Just after the vertical line, the point seems to be slightly higher than what they used to be, but it is fairly small. And in fact, this is not even detected by our test. Here, all the points are green, and because they are all within the fluctuation interval. The question is how to build a new test to detect these kind of problems. What we did is, instead of looking only at the one new observation individually, we look at several of them, like hn plus 1 up to hn plus k, and we use the average, and it's this average that we compare to the previous observations. Because we use the average, we can shrink quite a lot the fluctuation interval. So let's show me an example. Here, still the old observations in black, and in green and orange, we have the two series of 5 new observations here. And if you look at each of these new observations independently, well, they are all within the fluctuation ellipse, so you cannot conclude anything. There is no problem here. But again, if we take the average of these new observations, here the green average is inside the new ellipse, which is much more shrinked, and the orange average is outside. So the conclusion here is that the green points are normal and the orange points are an anomaly because the average is outside. So again, let's have a look at this test on real data. So it is the same data I showed you before, but here we use an average of 5 days, using a window of 5 days. And what we see is that the fluctuation interval here is much thinner, much smaller than what we had in the previous test. And thanks to that, we were able to detect this change. We have 2 points that are labeled in red. So yes, here we were able to detect this change. And we labeled, we investigated, and we found out that this was a bias upgrade on the cluster. All right. This plot, we have one of them for every node, and we have hundreds of nodes, and one of these plots for every parameters, and we have dozens of parameters. So this is really too many plots. So for that, we implemented an overview plot. Here this is for the one particular cluster, the diode cluster, and in the x-axis, you still have the dates, but on the y-axis, you have all the nodes of the cluster. It is very nice to see any global change that happens on the cluster. For instance, here we see that all the nodes at this date started to become slower. Here we see the cooling issue that happened on a few nodes, and here the cooling issue is fixed. And we can maybe distinguish a bit the bias upgrade I told you about. A few points are maybe different colors, but this is quite subtle here. But again, by changing the test and using the 5-day window, it's much better. Now we clearly see a lot of points colored in bright red, so the problem is very visible here. So to wrap up on the performance test, in the figures I showed you, it was only a test in one dimension, so using only one variable. But we also implemented this for the multivariable tests, and we use that on the coefficients of the linear regression, all of these coefficients. This is available online at this address. This is basically the landing page that you see here with all the nodes and all the parameters that are available. And now the question is, did we manage to find events that affected significantly performance? The answer is yes. We detected several events, so several bias upgrades of the clusters. The cooling issue I told you about. There were, in several occasions, faulty memory sticks that affected a lot the performance. And some power instability that happened twice on 2 different clusters. And the thing is that all these events affected significantly the performance and went completely unnoticed by both Grid 5000 staff and the Grid 5000 users, despite the effect on performance. So this means that using this kind of tests in production could be very valuable for everyone. Right, so I will conclude this talk now. First, back to our predictions, our simulations. The question is how to know if our predictions are faithful. This is not mathematical. This is not a mathematical theorem. This is not an algorithm that we can prove. The only way we can validate our model is to try to break it, to push the model to its limit and see if it's still faithful or not in these particular configurations. This is what we did during this thesis. We pushed the model very far, and in fact, we broke quite a lot our simulations. In several points, we had very good predictions on a particular calibration, on particular configuration, sorry. And then we changed the configuration and the predictions were completely wrong. So we had to investigate and to solve the issue. And now it works on everywhere. To be a bit more convinced that yes, it works, a few weeks ago I repeated the whole study from scratch on a new cluster from Grid 5000. I made new measures of DGM and MPI. I generated a new model. I made new simulation, new real executions to compare them. And yes, in the end, it worked very well. So now the question is where to stop, because here I tested only 2 different clusters of Grid 5000. Maybe I should try other clusters. Maybe also other applications, because I said that we could apply a similar approach to other applications. But in the end, it's quite a lot of work, firstly, and also quite a lot of resource consumption. Speaking about resource consumption, I would like to speak about this. It was important to me at the end of my thesis to try to estimate the carbon footprint of my work. So this is really a rough estimate, but I think the order of magnitude is accurate. First, I emitted about 8 tons of CO2 to travel, because I went twice to the USA. And then nearly 10 tons of CO2 just for computations. So the first question I would like to ask myself, and maybe you, is do we really need to attend conferences in person? Because here this defense is done remotely, and I think it works pretty well. But then what about computations? What can we do to try to reduce our computations? And these 2 mining core hours, about half of them were spent for the performance test. The test we use, we run on a daily basis on Grid 5000. So first question is how to reduce the amount of computations. First, maybe there is no need to do a full node installation at each time. So maybe changing the experiment procedures could help to reduce the whole time. Then maybe testing less frequently, for instance, only once a week instead of every day of the week. It could be enough to detect important changes. And then using a cheaper test, so maybe a shorter warm-up or maybe a less extensive coverage, because in our test here, we run DGEM on a lot of different matrix sizes, but maybe running it only on a few matrix sizes will be enough to detect a change. And then there is a question of who should be responsible of the test and who should bear the ecological cost of this. Because we could argue that the platform staff should do these tests, but then there is a question of what should they test? In my case, I use the DGEM function in my test because it's extremely important for HPL, but other users may rely more on memory intensive or disk intensive or network intensive workload. So in the end, the platform staff may have to run a lot of different tests. Then we could argue that each individual researcher should have to run their own tests, but here it could very quickly become redundant and quite a waste of resources also. This is a difficult question, I think, and I will keep it open voluntarily. A few perspectives for this work. I think this would be very interesting to apply our approach of predictions on the whole life cycle of supercomputers, starting from the design. When manufacturers want to build a new supercomputers, it could be very interesting for them if they had faithful predictions to build the best possible machine, most performant machine on a given budget. Then developers could use predictions in their development work for doing some performance debugging, for instance, because it's much simpler than doing some full-scale tests and much less costly in terms of resources. Then for platform staff, could be interesting when they do some maintenance or some routing upgrades to run a few simulations afterward as a truth, to compare the predictions to the reality and see if this changed or not. All right. Thank you all for your attention, and I'll be happy to answer any questions from the members of the jury.
Okay, thank you, Tom, for this very nice talk. I have a question now. Did you have a prediction model for your defense? Because you are perfect for the time.
No, I did not have a model. In fact, in my repetitions, I was a bit longer. But
okay, yeah, okay. So we start the discussion. For example, with the reviewer. So we have only one reviewer, Patrick. Perhaps you can start with the comments, your question, discussion with Tom.
Okay, thank you. So thank you for the presentation, Tom. So I was really happy to read your document and to review it. So it was easy to read, and I really appreciated the fact that it's really complete, because okay, you did some prediction, but you work on this whole experimental environment, as you mentioned, all the bias, all the platform changes, and so on. You developed some tools for that as well. And you didn't mention that during the presentation, but you had a tool for performance regression and being able to rerun batches of codes and stuff like that. So it was very interesting to see that in your PhD. So I just have a few questions. So one about the machines. How would you extend your work for more heterogeneous machines, like with GPUs or that kind of architectures? How would you see doing performance prediction with this kind of machines?
I think for this kind of machine, it's not necessarily a problem. You can still measure, for instance, the duration of computations like DGEM as a black box, exactly as we did, and then trying to model this just looking at the duration of these computations. In fact, we did it at the very beginning of this thesis. We tried to model the Stampede cluster in Texas that had Xeon 5 coprocessors, KNC. And so sometimes the computations were offloaded to these accelerators, and sometimes they were not. And so we just measure the DGEM duration for a lot of different matrix sizes, and this change, we could observe very well whenever this was offloaded to the accelerators, just in the durations. And so here we just have to modify our model and say to apply the same rules that they use, to offload or not, for instance, the computations, and to use this same kind of rules in our model. I don't know if it answers your question.
Yeah. Okay. Thank you. So it brings me to another question, because you said, okay, we can replace the DGEM if it's offloaded or not, and so on. That's good. So what about if you have more something irregular in your application? So for example, if the applications has more complex computation phases, or with the if statement and so on, or if the runtime is more complex, as you mentioned, if it's offloaded or not, if it's dynamic, how would you see the extension of your work for that?
Here we need maybe a lower level of abstraction, like emulating each of these if statements, for instance. It can become more tricky. First, it will be longer to simulate, probably, so which can be a problem if you want to reach quite a large scale. But then, if you really have this kind of complexity with, for instance, cores that do not exactly do the same thing as other cores. For instance, one core is doing a lot of memory-intensive stuff, and another core is doing a lot of arithmetical CPU-intensive stuff. Well, it can become quite hard to manage with a dynamic frequency scaling mechanism. But so for this kind of studies, maybe we should need to capture in our simulator more complex mechanisms of the computers, like the dynamic frequency scaling, like governors or etc.
Okay. So really extension to get more information, to get more metrics.
Yeah.
Basically.
Yeah.
Okay, and just maybe one final question is so about your experiments with the network topology. So I think it was on slide 10.
Yeah.
So you tried you simulate different topology to see if it was possible to get to change the switches and so on. So would you see a link with the job scheduler in your case, or is it completely independent from the job scheduler, like Slurm or PBS or something like that?
Do you mean using your work in a job scheduler, or
to get information from the job scheduler, or the job scheduler can use that? I mean, how would you see the interaction between, because for example, getting switches, being on the same switches or different switches, it can depend on how your job is scheduled on the different nodes, which are linked together at L1, L2, or whatever. So how would you see, the interaction between what you've done and the job scheduler policy, for example?
Yeah. I'm not sure we should use these predictions in real time, for each decision that your job scheduler has to make, because, all right, these simulations are much cheaper than real ones, but they can still be quite long. I'm talking about hours for the longer simulations. So it's not feasible to use that directly in the scheduler. But what you can do is do yourself your study in simulation, make some conclusions of what you observed, and then apply maybe some rules for your scheduler itself. I don't know if this makes sense. But
okay, so per application, trying to maybe adapt the scheduler policy, for example.
Yeah, exactly. Yes, depending on kind of applications that you observe on your platform.
Okay, thank you. That's it from me. Thank you very much.
Okay, thank you, Patrick. So the second reviewer is not here, Henri Casanova, but I read his report. This report is very positive. I read some sentences. For example, Tom make several important novel contributions and show a level of scientific and experimental rigor for the scientific contribution and experiment. So it is very positive. There is no question in the report I can ask to you. So now we can switch to another member of the committee. So I think Abhinav, you can ask a question, give some comment about the presentation and the manuscript.
Sure. Sorry,
thanks.
I'm unable to turn on my camera. It just keeps trying and then says fails. Thanks,
Okay.
Tom. This was a wonderful presentation, and I also liked your work in your thesis. I think few people have tried to model variability and performance in face of variability and noise. I think this is very good work. I had a few questions. So if I understand correctly, when you model the computation, these are either analytical models or regression-based models. Are these then implemented in SimGrid?
Well, yes, these are regression models, and they are not implemented in SimGrid. What we do is I just made a few modifications in HPL code, and so I replaced at the location where they call the gem, I replaced this by like a slip of the appropriate duration.
Mm-hmm. Okay. And then I had a similar question about the communication part, like how is that being done through SimGrid or through some models that are outside of SimGrid?
No, the communication part is done in SimGrid. We only had to modify SimGrid at some point to in the CD where we try to model the randomness in the network, some variability. Here, this kind of thing is not supported currently in SimGrid, so we had to hack a bit of thing in the code. But all the other things are in SimGrid, yes.
Okay. So yeah, for example, this plot here on slide 14, in this you change the network configurations in SimGrid and then
yes, this one, in fact, when you use SimGrid, you just have to pass a file that describes your platform, and we just change this file. We say, given the factory notation, we change the number of switches to the top level. But yes, this is supported in SimGrid.
Okay, all right. I think those were my questions. Thank you, and again, it was a great talk.
Thank you.
Okay, thank you, Abhinav. So we are in US with Abhinav. Perhaps we can continue in US with Camille.
Thank you. Let's go to the West Coast.
Yeah.
So I think I'm going to second Patrick's comment. I think your work is very complete and very thorough. And I appreciated in particular the part where you say, okay, we observe this. Why do we have this? And in particular, when you talked about the overheating of the platform, where when the reality didn't really match the models and the simulations. And my question is, I will be fast because there's a big committee. But my question is regarding the adaptation of the model and how you can adapt to the platform variability. And so in your particular case, it was a matter of overheating that was slowing down the machines. So, but you know that through the execution of an application, there can be such variabilities. For example, if you have parts of some processes that compute something, or machines that overheat the machines temporarily, or we know that in the computation centers you can have jobs that are very computation intensive and that will create some heat in particular places of the cabinet and can have an impact on neighboring nodes. Sorry. So my question is, if you have variabilities at runtime, and you have an idea of the distribution of this variability, etc. Can you have a model that through the execution varies?
Yeah, it would be interesting to do, obviously, but more difficult, I think. In fact, I'm not even sure if it's... Yeah, this may be possible with the current state of SimGrid. Well, you could imagine a simple hack to do that would be to change our model, our DGEM model, depending on the timestamp, and to say, like, yes, after 10 minutes of simulated time, you will get 10% slower. Here, this will be easy to do. but maybe not very realistic, depending on what we want to model. Yeah, I'm not sure how I will approach this. What would be the best approach to model this in SimGrid in a proper way, in not a hacky way?
Okay, well, thank you.
Okay, thank you, Camille. Perhaps we can come back in Europe with Germany. Christian?
Yes, I can only repeat what was already said about your thesis. So I was really impressed by the work and I think scientific rigor in the like in the treatment of the statistics and the analysis. I have never seen a work that is so deep and so thorough. So congratulations on this really nice work. Some of my questions have already been addressed. So let's move to some maybe a new topic. So I'm also heading an HPC center where we procure HPC systems, right, on a regular basis. And I was wondering how this method of performance prediction could be used to select a suitable HPC architecture. So for instance, if you look, there is different SKUs, right, of say you have a certain CPU, AMD Milan, and you have different numbers of cores and frequencies. And then the question is, if you would like to optimize, for instance, achieve a certain LIMPAC performance, could you use this approach to select the most desirable CPU or do a prediction? Like what the point I'm trying to get at is, in your work, you assumed that you have a cluster and you have measured this node-specific variability. Whereas typically you cannot do this experiment if you want to extrapolate for future technologies. You usually only have a few nodes or just a single processor. Can you still apply, or do you have an idea how the method could be used to predict performance of future systems that you cannot profile and measure?
Yeah, so if you still have access to a few nodes, maybe not the whole machine, but only, I don't know, a dozen of them, and if this sample is representative, you can very well extrapolate it to a given size. And in fact, this is kind of what we did in this use case study here that I'm showing. We took our local cluster that has 32 nodes, and we extrapolated to I'm not sure, maybe 256 nodes or even more. I'm not sure. Using some statistical techniques were quite simple. So yes, if you have a few nodes at disposal, I think this is not a big problem. You only want your sample to be representative. Now, if you do not have any node at your disposal, because this is really like future architecture, obviously it becomes trickier and just like a guesswork to try, maybe start from an existing model from a processor that is quite close from the one that you want to model, and to try to tune by hand the parameters of your regression because if you hope that your performance will be, I don't know, 20% higher at the cost of maybe a 5% increase of variability, that we can adopt our old model to try to capture this. Mm-hmm. That's how I will do this, I think.
Mm-hmm. There was one area where I was not so sure. So essentially what you do is to make your simulation feasible is you need to throw away a lot of things, right? You don't do any computation and you avoid the communication and the memory allocation. You need to do a lot of abstractions, right? So on one hand, this is needed. On the other hand, this gets into conflict with the computer architecture where you have effects like caching, multi-level cache hierarchies, you have caching in the file system. Still, your predictions are very accurate. Can you explain why this is? So despite ignoring so many effects that need to be exploited in the computer architecture, you're still very accurate.
Yeah, I think this is because in HPL we spent maybe more than 95% of the time in the dgem function, and this function is extremely CPU intensive and extremely well implemented, very well optimized. So maybe you do not have so much cache effects or cache problems in the usual workloads of HPL. So if we did problem that we might have on other applications that use maybe more complicated functions or maybe less optimized functions, is exactly what you say, is that we may miss some phenomena of memory issues or disk issues or network issues that were not necessarily present in HPL.
Okay, that's it from my side for a moment. Thank you.
Thank you, Christian. Perhaps we can go with Amina. Sorry. You are in Paris or Bordeaux, I don't know where.
Thank you,
Amina.
Jean-François. Amina. Can you hear me?
Yeah.
Yeah,
yes,
perfect.
Okay. So I want to say, like everyone else, you did a very great and impressive work. Your presentation was very clear, and the manuscript was very, very interesting. And I liked how you were doing some investigations on why everything was not the way you expected it to be. And being one of the last juries member to talk, most of my questions have already been answered. So I only have very, very few questions. So maybe you didn't really address this part in the presentation, but in your manuscript, you talked about, well, we also see it here, reproducibility. So, and it was kind of depressing because most of our already published work will most likely not be, our experiments, we will not be able to reproduce them now. So based on your experience, is there some advice you would provide us on what to do?
Sure, a lot of advices.
I should take notes then.
First thing is like automate everything because it's when you do experiments by hand, then you will make mistakes because humans make mistakes, and then you will 6 months later you will have forgotten what you did. And so if instead you use some good experiment engine, then it will be much easier to just rerun your experiment again. Then during my thesis, I used a laboratory notebook. So whenever I did some experiments or I read a paper or etc., I wrote it in my notebook. And so by doing so, well, I was able to go to some very old stuff like I did 2 or 3 years ago, just to look at what I did at the moment and what was my thought process, my conclusions, etc. And I think this is one of the things that I did in this thesis that helped me the most to achieve a better reproducibility.
Okay, but on the part where you study how the nodes change, what happened, you showed that at the end, like for instance, BIOS update or whatever. For that, there is absolutely nothing we can do, right?
Well, you cannot prevent the platform to change.
Yes.
I think it's not up to you. So what you can do is like regular tests, similar to what we did, to be at least notified when this happens. Or maybe even simpler is just at the beginning of your experiment, run some micro tests to have some ground truth. So you do not maybe have to run a test every day, but just one test at the beginning of your experiment, like a 5-minute stress, and measure the performance will be maybe enough to see if there is something important to you that changed or not.
Okay. So that was my question, and that's it for me. Thank you, Jean-François, and thank you, Tom.
Thank you.
Okay, thank you, Camille. So perhaps we can complete with Arnaud. And don't forget anybody, I hope. Yeah.
So as you may imagine, since I'm the PhD advisor, I don't have much question.
Okay.
So I guess I'll only say kind words. So just to say that it's been a great pleasure to advise Tom. As you may have guessed from the defense, Tom is extremely rigorous and perseverant, and it was essential for such work. So the platforms ended up being much more complicated than I initially thought. And as I was saying, oh, well, Tom, why don't you try this and this? It should work. And Tom kept coming back to me and telling me, well, you know, I think there's something weird and it's more complicated than you thought. So just see what I found. And I was like, oh no, man. So, and it was only possible thanks to his rigor and his will to never ignore any details. So Tom, I truly hope that your work will convince our community that predictive simulation of HPC system is not just possible, it's also a viable option. Last, as you may imagine, I also fully share your ecological and ethical concerns. So I just want to say I'm really proud of the scientist you've become, especially as your work really illustrates the importance and the difficulties of empirical studies in computer science. So just thank you, Tom, for letting me be your advisor.
Okay, thank you, Arnaud. So I conclude. So I have one remark. So I appreciate very much the presentation. The slides were very nice. Okay, it's perfect. I have a question about memory because I suspect that variability mainly comes from memory. Did you think it will be useful? Because I know it's difficult. It's part to understand the memory behavior. It's very difficult. But do you think it may be useful or necessary, perhaps, to investigate this kind of study on memory? Perhaps to understand some variability.
Personally, I'm not so convinced that memory could be the cause because well, the gem is more like a CPU intensive function, and in my experience, I had the feeling that it was more about frequency and temperature problem that may explain variability that we observed, like some nodes had a slightly lower frequency than others because of, I don't know why, maybe temperature, maybe the processor is not exactly, is not perfect. And these nodes with slightly lower frequencies had also lower performance. And that's why I think this is more of like really a problem of the processors and not memory. In this application, maybe other applications, of course, the memory could play a big role, but here in HPL, I think this is a processor.
Okay, but you think that temperature and frequency, there is no link with memory?
There could be, yeah.
Yeah.
If there's, you could imagine that one memory stick will hit a bit more than the others, or will consume more energy than the others. In fact, yes, I've seen a paper where when they decrease the frequency of the memory sticks, this allowed to increase slightly the frequency of the processor and to get a better performance. A paper from Amin Ali Al-Mushna, I think. So yes, it could play a role also. Yes.
Yeah. Okay, thank you for your answer. Okay. There is no other question, so perhaps the committee can deliberate directly. So I think you have to leave the Tom, and perhaps Arnaud can contact you by phone or something, so you can come back after the deliberation.
All right, so for those who are still on YouTube, I invite you to come on the Gather. I will just put a link on YouTube chat. Wait for it. Wait for it. Here's a link in the chat if you want to just some informal talk, informal gathering on Gather. Je change ça.
Donc on repasse sur YouTube, c'est ça?
Ouais, on va repasser sur YouTube. Et je vais quitter du coup Gather. Et on reviendra sur Gather après la délibération.
Ouais,
Tac.
You are now muted.
Tom, you are connected?
Nearly.
Take a bit of time before
Yes.
everything comes back.
Seems to work.
And we have to wait also for restarting the
microphone.
He's sharing his screen on YouTube, so it's funny. We are inside.
Okay. Okay.
You are now
It's
unmuted.
okay, Tom?
Yeah, can you hear me?
Okay, perfect. Okay, so the committee discussed about your thesis, and so I will give some information about the report and for your thesis. So your research domain is the modeling and predicting performance on large-scale HPC and parallel applications. This thesis built on a significant amount of experiments performed in a rigorous way. There is a good balance between experiment and theoretical work, trying to focus both on statistical model and developing methodology for conducting rigorous experiments. The committee has been impressed, apart from empirical and statistical rigor, by the careful and well-crafted data visualization to convey the right intuition even using high-dimensional data. So you also show interest in application of environmental and societal aspects of your research. By transcend technical and scientific aspect, and you demonstrate your ability to step back and to develop an interesting perspective on your work. For example, regarding your use of laboratory notebooks or experimental engine. So during your defense, you show a very good and very wide knowledge of both HPC domain, statistics, and an impressive understanding of technical detail. So you made a very pedagogical and didactical presentation and did a great job in selecting the most important parts of your research to present them in a comprehensive way. The talk was very fluent and pleasant to follow, and the presentation was backed by good illustration and sketches. You demonstrate a good understanding how your work and contribution fit in the current HPC domain that goes beyond solely experimental with HPL. This presentation has confirmed the quality of your contribution and of the result. So you gave also very relevant answer to the numerous questions from the committee about your work and more perspective question or architectural or co-design and modern HPC application. Your answers were not only relevant but also confirm your deep understanding of the topic. For all these reasons, the PhD committee decided unanimously to attribute you the title of Doctor de l'Université de Grenoble-Alpes with the field of informatics, computer science. Okay, congratulations, Tom. Good luck for the
Thank
next
you.
month and in the next year. Okay.
Congratulations.
Thanks a lot. I just would like to address a few thank you. So, first of all, obviously, thank you to all members of the jury to accept to be here today to attend my PhD defense. And in particular, the two reviewers, Patrick Caribo and Henri Casanova, who made great comments about my manuscript, which were very insightful. Then thank you to all the people that worked on SimGrid and Grid 5000 because I used these two resources a lot, and they were very helpful and very friendly always. So great thanks to them. Obviously, thank you to the Polaris and DataMove teams in which I spent the last 4 years. And so they were extremely welcoming, and I'm very grateful to have been able to do my PhD with them. The days are much shorter when you do a lot of coffee breaks and barbecue in the evening. Then, obviously, a huge thank you to you, Arnaud, for gratefully accepting me as your PhD student. I've learned a lot of things during this thesis, obviously, and also, but even more so, it was a real pleasure to work with you, and I hope that we'll be able to collaborate in the future. And finally, to conclude, to keep it short, huge thanks to my family who were able to help me, to support me during these years. In particular, my niece, with whom I'm very happy to share my life, and my baby, Yael, who doesn't understand yet what I'm saying, but just a great baby. Thank you all, and if you want to join us virtually on Gather, so I've put a link on YouTube, and I will put the link on the chat here, because unfortunately there is no food or drink because of this crappy COVID situation, but just hang out to be nice. Thank you all. Just put the link.
Thanks again, Tom. And thanks to all the members of the jury for being part of all this. I'm grateful.
Yeah, if you want to join.
Okay.
So you've cut the YouTube stream?
Yes, I will cut the stream and Gather.